just as it says there, this logic, cryptography, graph theory, programming, all kinds of things it's a basis for. At UMSL, it's kind of a gateway course between what are considered freshman and sophomore math courses and junior and senior math courses. It's a good. Hopefully, you got that to look forward to. Yeah. It'll be fine. All right, let's get started here. Just want to point out there's a flyer here for a discrete mathematics course that can be offered at Merrimack in the spring, and it's got an interesting variety of topics that are included in it. Some of it's logic, different kinds of problem solving. So it's a lot different than calculus, all right? And it's a lot different than just plain algebra. So, you know, I encourage you, if you're interested in continuing in math or in computer science, to look into it as a possibility for you. Okay. Now, we've been talking about, one thing, let's get this out of the way. Please turn in your homework number 5, and then you should have the take-home quiz and the homework number 6, and that'll be due on Wednesday when we have the test. And the test, as I said, is on Wednesday. I sent out an announcement on that just in addition, and that's on everything in Chapter 7 except for 7.6 and 7.7. I'll be covering those just real briefly today. You won't be tested on those. You also have available a practice set, facts and formulas to know for the test, and I will be posting the practice set. I won't be grading, but the solutions will be posted, full solutions, on Sunday afternoon on Blackboard. All right? Okay. I want to point out that, you know, we might get the false impression that because we've been integrating all these different kinds of functions, that, heck, we can just integrate anything. And in fact, unfortunately, that's not the case. There are a lot of functions that we can't get the antiderivative for, or the antiderivative cannot be expressed as, say, a combination of radicals and logs and exponents. Those are called fundamental functions. Sometimes the integrals are expressed as infinite series. So I just want to show you just some of these things that you think might be integrable, but really aren't. Something like 1 over the natural log of x dx. No can do. E to the x divided by x. Same thing. E to the x squared. Nope. The sine of x squared. The square root of x to the third plus 1. Not x to the square plus 1, x to the third plus 1. Sine x divided by x. Just a few examples of functions that we cannot, with the techniques that we have available to us, cannot get the antiderivative of. Okay? More things, yes. If we learn more things, yes, Jenna, then we could take a stab at them. All right. All right. What I want to just talk about briefly here is the next section, section 7.6. And here I'm just going to put my notes up here on the board. This is about using tables and maybe a computer algebra system to get an antiderivative. All right. And I have an example up here. Consider the integral of x times the square root of x squared plus 2x plus 4. And, okay, we could figure this out with our techniques, but we can also use integral tables. Now, your book has a few antiderivative formulas. It's got actually a couple of pages of them in the back of the book. Now, I used a book that has 40 pages of antiderivative formulas, but there are also books that have hundreds of pages of antiderivative formulas. All right? So what I want to show you what I used here for this is I used these two formulas here from this table, and I'm not certainly going to read all that off to you, but those are the two things that I used. Notice this one is, you have to get that's in the right format. Notice this one is x times the square root of ax squared plus bx plus c. That matches the the integral that I have. So that's your first thing, is to find something that matches the pattern of what you want to find. And then it gives me this nice short little formula for what this is equal to, all right? And notice as part of this formula, it has another antiderivative as part of the formula. So then I went to another part of the table and found out what that antiderivative is equal to, and we have the formulas there. So sometimes you have to go to a couple different places in the tables if you're going to use this method of looking up in tables your antiderivative. Now, what I then ended up doing here is I replaced my A with a number 1, my B with a number 2, and my C with a number 4, and I went through this process of filling in all of these, and please don't write this down, and I got my antiderivative, all right? So it's a matter of then filling things in and not messing up the algebra. Okay, so this is one way of getting antiderivatives, is using these tables, right? But you have to use the correct formula. Now there's another way, and that's using what are called computer algebra systems. What we're talking about there are programs that are used by engineers and scientists and scholars. Mathematica is one of them. Maple is another one. There are others besides that. Those are the two that I'm most familiar with. So I have a Maple on my computer at home. So let's see, what are we doing here next here? So basically, let me just show you. Using Maple, I put in, next to the little cursor there, I put in that I want to figure out the antiderivative of the square root of x plus 4 divided by x, all right? Then you hit enter, and then it whirs a little bit, and then hopefully you get your answer. And so this is what came out as my answer then in Maple for my antiderivative, right? And personally what I do is before I present things in class, and when I am doing problems for tests and practice sets, I'm going to test my solutions with the computer, just to make sure that I'm doing it right, all right? Because I don't want to present you with incorrect stuff. So anyway, that's a very common tool. If you are actually ever going to be employed where you're using calculus in engineering as part of as your work, you're certainly not going to be doing a lot of this stuff by hand. You're going to be using these kinds of computer systems to get your answers. However, the thing is, if you don't know up here the basics of what we're talking about, you'd be a dangerous person to be running these systems, to be doing this. You've got to know what the answer means. In other words, you have to take a basic calculus course, okay? But anyway, these are two very handy ways of, in particular, the latter way of getting antiderivative in, shall we say, the real life world. All right. So that's all I want to talk about in section 7.6 is just that awareness. All right. Now, I didn't want to do that. Okay. The next section then, 7.7, this is where we approximate the value of a definite integral. It's called, the title of the section is called Approximate Integration. And if we had more time, I'd like to actually have spent a little more time than this on this, but I have to go within, cover what we need to cover. So the thing is, let's look at something like, okay, say we want to get the antiderivative from, say, 1 to 5 of e to the x squared dx, or maybe something like the antiderivative from 2 to 7 of e to the x over x dx, or something like from 1 to 10, the antiderivative of x to the 3 plus 1 dx. Those were all functions that we can't get the antiderivative of. At least not right now we can't. Because normally when we do a definite integral, we get the antiderivative, and we plug in the top limit, and we subtract off the bottom limit. But with these functions, we can't even get the antiderivative. All right. So we still have a method available to figure out numerically what the value is of this definite integral. We can approximate to as much of a degree of accuracy as we need. We can approximate the answer by dividing the curve of the graph into sections. By dividing the curve of the graph into sections. Now, I want you to understand that here we are strictly talking about definite integrals that have the upper and lower limits. Definite integrals only. All right. Okay. So let's see. I've got something here that I can get up on the screen here. All right. And let me get this so that you guys can see it. Let's see. We need to have the PC go to all of them. Okay, good. All right. All right. And they should be able to see that also. All right, so approximate integration. So here we have a function that's bigger than 0, and we have a definite integral here from, x naught to x sub 4. And basically, we're approximating, we know that the definite integral, remember, is the area under the curve, right? That's what it represents. This is the area under the curve, under the graph. So we can basically divide this thing up into some equal width segments, and then we get a series of rectangles that we can use to try to approximate the area of the curve, under the curve. So basically what we're doing now is adding together a bunch of rectangle areas. And of course, the more rectangles you have, the closer the area is going to be of the rectangles, the closer it's going to be to the actual area under the curve. All right. So there are 3 different rules that the text talks about for doing this. The first one is the midpoint rule. And this is where on each of those rectangles, you pick the middle of the rectangle right there in the center, and you draw the top of your rectangle right there at the center point. So we see that each rectangle, the top horizontal point is where the middle reaches the graph. And so this actually gives us a closer approximation if we use the exact middle of each rectangle as the top part of our rectangle when it hits the graph. And again, by making more and more equally wide rectangles, we're going to better approximate the area under that curve. This here is the actual mathematical formula that is used when you are doing the midpoint rule. Notice that this delta x, that is the width of each rectangle. You want to have the rectangles have identical widths. And then these points here, these are the values of the function at that midpoint section. So we're basically just adding together a bunch of areas of rectangles in this rule. All right. Now the next rule is called the trapezoidal rule. It's not quite as good actually as the midpoint rule. Here, instead of using rectangles to approximate our area under the curve, we're using trapezoids. We know trapezoids they're parallel sides, but they're unequal in length. So here we're dividing up under the area under the graph. Here we have 4 different trapezoids, and there is a formula for calculating from geometry, from calculating the area of a trapezoid. So we add those areas together. Here is the actual mathematical formula for the sum of all those areas, and I won't really go into that, but I do want to point out again that the delta x here, that is the width of each trapezoid. All right. Now the best rule, the most accurate rule, is the third rule. It's called Simpson's rule. Instead of using rectangles or trapezoids, we use parabolas for each of the little sections. Basically, we divide up again from A to B, we divide it up into equal areas, but this time we want to divide it up into an even number of sections. So right here, we divide it up into some even number of sections. And then what we do is we take the endpoint, the 2 endpoints. We have an endpoint here and an endpoint there, and then we also have a middle point of the interval, and we calculate the function values at those 3 points. Now, if you have 3 points, you can calculate a parabola, which is a quadratic function that basically approximates those 3 points. So what this red line is here, it's the approximating parabola for this particular first section. In this second section, we again have an approximating parabola, and in this third section, we have another approximating parabola. This gives us a closer approximation because now it's not just linear. There's a flow to each of the tops, which can give us a closer approximation to the area under the curve, all right? Okay, so this one has a more complicated formula, as you might expect, and by the way, it's named after an English mathematician. Again, we have the delta x, which is the width of each section, but then we have a pattern of coefficients here that is being multiplied, and this is the pattern is 1, 4, 2, 4, 2, 4, 2, and all this, and then 2, 4, 1. So there's a pattern of coefficients that are involved. The text goes into how we derive this pattern of coefficients, but we're not going to go into that. So what I'm really wanting to leave you guys with is this, since we're not really doing this section, I want to leave you with an awareness that there are, in this case, at least 3 different methods that if you're unable to actually figure out by regular means what the value is of a definite integral, you can use these methods, and most of the time, let's face it, you're going to be using a computer to do this stuff. Nobody's going to be, in the real world, going to be multiplying all this stuff out by hand because we make mistakes. All right, so that will then give you an approximation to whatever accuracy you need for your definite integral. Okay, using these methods. Any question on these things? I know it's very quick. All right. Okay. Let's see. Is that it? Yeah. All right. Okay. Then we're going to get into the last section here. And I need for you guys to see. I just want you guys to see this. Yeah. Okay. All right. Okay. So the last section is 7.8. And the topic here is improper integrals. And what in the world do we mean by an improper integral? Okay, 7.8. Improper integrals. Okay. Well, there are 2 classes of these, and I'm going to first talk about this one. So there are 2 types. And the first type is this, A, where one or both of the limits of integration is either infinity or negative infinity. So where one or both of the limits of integration is either plus infinity or minus infinity. All right, so that's what we're going to talk about first, and then we'll get to the second kind after this. So here's the first example. Antiderivative from 1 to infinity. Okay, so we have infinity as our upper limit of integration of 1 over x squared dx. So how do we handle this? Since we have infinity, we're going to use a limit, right? So to evaluate this, we look at the antiderivative from 1 to, let's call it the letter t, where t is some number that keeps getting bigger and bigger, of our 1 over x squared dx, and then we evaluate the limit as t approaches infinity. And then evaluate the limit as t approaches infinity. All right. Okay. So let's go on and do that here, see what we get. So we're going to have the limit, Lim, as t goes to infinity. So that's the first thing we're going to be writing here. The limit as t goes to infinity. Now we're going to have the integral from 1 to t instead of infinity. Then we put our expression 1 over x squared dx. All right. Okay. And now, just like with any kind of integral, we get the antiderivative of this. And the antiderivative is going to be minus x to the negative 1 power, or minus 1 over x when we evaluate the antiderivative. And then this again, I should have left myself more space. We do the limit as t approaches infinity of this antiderivative where it's evaluated at 1 at the bottom and t at the top. Okay, so again, we keep that limit notation, and we still use the t. All right, so now let's plug, let me write this before I forget to, the limit as t approaches infinity, and now we plug in our t and our 1. So here it's going to be minus 1 over x, so it's going to be minus 1 over t, minus, and then plugging in the 1, I'm going to have minus 1 over 1. All right, double negative there. Okay, now, so let me just rewrite this. The limit then as t approaches infinity of minus 1 over t, and the second thing just gets replaced with a plus 1. All right, now what is the limit of minus 1 over t as t keeps getting bigger and bigger and bigger and bigger?
0.
0, right. As we're dividing by bigger and bigger and bigger numbers, we get a smaller and smaller and smaller result. So this limit is, the first thing is 0, that's our limit there, but we also have the plus 1. We don't want to drop that, so our answer here is 1. That's the value of that improper integral, 1. Okay, now, since this equals a finite number, we say that it converges. Since this equals a finite, I guess that's kind of a redundancy, isn't it? A finite number. But anyway, since this equals a finite number, we say, oops, let's go up here with it. We say that it converges. Quote unquote, converges. All right. Let's look at another example, and we're going to get a different kind of result. So the second example that we're looking at is this. Now we're going from 1 to infinity, but our function this time is just 1 over x dx. All right. So this is going to be equal to the limit as, again, t goes to infinity of our new integral here from 1 to t of 1 over x dx. Right? Okay. And we all know that the antiderivative of 1 over x is the natural log. So this is going to be equal to the limit as t goes to infinity of the natural log of the absolute value of x, right? And we're going to be evaluating it at the bottom at 1 and at the top at t. Notice how I keep continuing this notation here of the limit until we find or don't find the limit. I keep repeating that. Okay. So let's plug in the t and the 1 here. So again, I am repeating this notation. The limit as t goes to infinity. Now, the top one is going to be the natural log of t. Since we're talking about positive numbers, I don't have to put that absolute value in there. Minus the natural log of the number 1. And of course, we know that the natural log of the number 1 is 0. All right. Now, the natural log function, what's its limit? What does it tend to as x gets bigger and bigger and bigger? Infinity. If this is what the function looks like, the natural log function, it builds slowly, but it keeps growing. That's the way it goes that way. In the other direction towards the y-axis, it goes down, 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 down. So this limit then is infinity minus 0, of course, which is infinity. Now, since this limit is not a finite number, this is said to diverge. Okay, so since this limit is not a finite number, we say it diverges. We say it diverges. D-I-V-E-R-G-E-S. Okay. So it's kind of interesting. When we have 1 over x squared, we get an actual area. Notice this is what this means here. This first thing means. This means that, from the first example, that the area under 1 over x squared from x equals 1 to x equal infinity is equal to, what did I get? 1. But the other one said that the area under 1 over x from x equals 1 to x equals infinity, well, that one equals infinity. That's a pretty big difference, isn't it? It might be surprising that there is such a big difference. So what we have here, let's see, okay. It's basically just a comparison here of the two functions. The one on the left is 1 over x squared. The one on the right is 1 over x. Now, the 1 over x squared just has a finite area. Now, notice that because we have an x squared, that denominator, because it's a square, is going to keep getting bigger and bigger, a lot bigger than just plain old x. So this thing starts, shall we say, bending down to that x-axis a heck of a lot faster than the one on the right. In fact, it goes down fast enough that its area is only equal to 1. But this one hangs in there, and it actually has an infinite area underneath it, right? So it doesn't seem like there's that much difference, but there is. Okay, so one is convergent, the other one is divergent. All right, we okay with that? Those two first examples of how we do that. Use a limit. Okay, let's then look at some more. Okay, let's evaluate this one. Antiderivative, now this time we have minus infinity on the bottom. From minus infinity to 0 of 1 over 1 plus x squared dx. All right. All right. So first of all, the first thing I want to do, if I'm going to work this thing properly to show proper thought processes, I want to represent this as the limit as t goes to this time t is going to negative infinity, not to positive infinity. And when I draw this, am I going to put the t on top or the t on the bottom? Top. Bottom. 50-50, Jenna. No, the bottom. Look at the original integral. The integral has negative infinity on the bottom. That's where we're going to want to put our t, okay? Because it's on the bottom. And then on top we put the 0. All right. And then we put our expression 1 over 1 plus x squared dx. All right. So now then we evaluate the antiderivative, and hopefully we're all going to definitely know this by Wednesday, that the antiderivative of 1 over 1 plus x squared is the tan inverse of x. All right. Basically, I'm using that formula here. That it's on your formula sheet there, that 1 over x squared plus a squared dx, that antiderivative is 1 over a times the tan inverse of x over a. In this case, our a is equal to the number 1. So that's where we get tan inverse of just x as our result. Oh, and of course I didn't leave myself enough room. I was so wanting to get that antiderivative in there. We still have to continue with the limit as t approaches minus infinity. So minus infinity. And now here's our antiderivative. And now we put the t on the bottom, the 0 on the top. Okay. All right. So let's plug in the numbers here. Well, or try to. So this is going to be equal to the limit. Again, I keep this notation. Limit of t goes to negative infinity. Now we plug in the 0, so it's going to be tan inverse of 0. What is tan inverse of 0? It's 0, yeah. But the question is, what angle is it that has a tangent equal to 0? And that's 0. Okay, so this is going to end up being 0. And then it's minus the tan inverse where we plug in the t. All right. Okay. So let's write this again. So we have the limit as t approaches negative infinity of minus the tan inverse of t. So what we really need to find out then is this. What is the limit as t approaches negative infinity of that tan inverse of t? Okay, first of all, tan inverse is an angle between what and what? Negative pi over 2 to positive pi over 2. That's the range of the tan inverse. Now here we're talking about an angle then whose limit approaches negative infinity. So are we going to be talking about going to the positive pi over 2 or to the negative pi over 2, where we have a negative tangent? We're talking about an angle that's going to have a negative a tangent value that is negative, and it keeps getting more and more and more negative. Negative pi over 2, right. Okay? We see that? Okay. Then I assume we see it. All right? Negative pi over 2. So therefore, when we go back up here, my limit is the negative of that. So we do have a double negative here. So it's minus negative pi over 2. And so our answer then is a positive pi over 2. Okay? So it's convergent. And I did put on your formula sheet, I did add that in as a handwritten thing on your formula sheet, because I have some limits. If you look in the improper integral section, which I think Jenna had done, or maybe not, but you do see these limits there. Also, for you folks at Eureka and Lafayette, I did add in the improper integral thing for your facts and formulas to know, I did put this particular formula down, and then there's another one that I also put down. What would be the limit as t goes this time to positive infinity of the tan inverse of t? And this time it would be the positive pi over 2. So this is positive pi over 2. So that's also there on the sheet. Okay. All right. Okay, what if we have this then as our integral? Let's see. What if not only we have an infinity on top, but this time we have a double whammy, and on the bottom we have a negative infinity. So we have it in both places. the antiderivative or definite integral from minus infinity to plus infinity. So now we have it both places, and it's just, I'm going to just use the same function, 1 over 1 plus x squared. Now, how do we evaluate something where we have it in both places as infinite? Plus infinity on top, negative infinity on the bottom. This is what we do. We split it up into two integrals, split into two improper integrals, like this. So we would start with minus infinity, but then I have to pick some number. I'm just going to say some number a. So I'm going to put down here where a is any real number we choose. Is any real number we choose. And then I put my expression, 1 over 1 plus x squared dx. But then I have to have a second one. Now this one will start at that number a, and it'll go to the positive infinity. So I split it up into two. And then what we have to do then is evaluate each of the integrals. Evaluate each of the integrals. So this is the first thing I want you to get clear. When we have minus infinity to infinity, oh, what is this? Okay. All right. Brian, I'll get to that in just a second, okay? So this is what we have to do then. Let's choose, we can choose a to be any number. I'm going to pick 0. That's kind of an obvious number between minus infinity to infinity. So we're going to split it up like this, minus infinity to 0 of 1 plus x squared dx, and then the other one is going to be plus 0 to infinity of 1 over 1 plus x squared dx. All right. Okay. Now just now in our previous example, we saw that this particular, from minus infinity to 0, the answer is pi over 2. And that's from our previous example. Now we're going to get the exact same thing from doing it with the other one, but let's just go through the process here. So this other one then, from 0 to infinity of 1 over 1 plus x squared dx is equal to, well, let's see, we've got the infinity on top, so that's going to be the limit as t goes to positive infinity of 0, from 0 to t of our antiderivative of 1 over 1 plus x squared dx. All right. All right. And so, same kind of process, we're going to get the antiderivative. So again, we repeat this notation, the limit as t goes to infinity. Now again, we know our antiderivative is tan inverse of x, and we put our limits, but we put our limits as 0 on the bottom and t on top. Okay? So then we plug in the bottom and top limits. We still keep this limit notation going here on the left, and so we plug in the top, tan inverse of t minus the tan inverse of 0, which is equal to 0. And then in fact, I had just written this formula down here. The limit as t goes to positive infinity of the tan inverse is going to be pi over 2. So our answer here, pi over 2 minus 0, or pi over 2. So that is, going back up here, that's the value of the second part of the process. So we add those two together, pi over 2 plus pi over 2, and we end up getting that our answer is pi. Okay. so it's obviously convergent. All right. Let's see. I want to answer your question, but I'm going to give me a little bit more time, and then I'll tell you guys what the question is. All right. Now, one thing I want to tell you right now is, okay, when we have to separate it out into two, like we did just now, this is a fact. Fact. The integral from minus infinity to infinity of some function dx is convergent only if both the first one from minus infinity to some number a, that's the first one, only if both that one and the second one from a to infinity, only if both are convergent. So if we're doing a problem like this from minus infinity to infinity, and we are separating it out into two, and say we're working on the first one, and that limit turns out to be infinity, we can stop right there. The answer to our question is this: the original integral is divergent, because the first one that we worked with is already divergent. We don't need to go any further, all right? If one of the two is divergent, we can stop, right? And I'll have an example of that. Let's see. I think, let's work on this, and to answer Brian's question, let's look at the integral from something obvious that we know is going to diverge, from 0 to infinity of x to the third dx. Okay. I don't think it takes a whole lot of thought to realize that this thing is going to have an infinite area to it. But let's work it out. This is the limit as t goes to infinity of the integral from 0 to t of x to the 3 dx. All right. Okay, well, we can get the answer. So this is the limit equals the limit as t goes to infinity. And our antiderivative of x to the third is, let's see, do I want x to the third? Actually, let me go back here. I think what I really want in order to answer the question, let's go back and let's have it be x squared, all right? No, wait a minute. Sorry. Before I write anything more down there, let me think. No, I was right the first time. Let's go back to x to the third. Sorry, guys. All right. So the antiderivative of x to the third is x to the 4 divided by 4. And we're evaluating it from 0 to the t. So that's going to be equal to what? The limit, again, as t goes to infinity, we plug in the top number. That's going to be t to the 4th over 4 minus, and then the bottom number is 0 to the 4th over 4. All right. So we can figure out that as t is going to infinity, t to the 4th over 4 is certainly going to go to infinity. So this is divergent. All right? And similarly, the antiderivative from minus infinity to 0 of x to the third dx is also going to be equal to infinity. It's also going to diverge. Okay. Now, this is the question that Brian asked. Brian asked, well, instead of splitting it up separately, so instead of splitting up from minus infinity to infinity, and I'm going to use this function here, x to the third dx, as minus infinity, say to 0, plus 0 to infinity. Instead of splitting it up like we're supposed to, why don't we do this? Or why can't we do this? Say the integral from minus infinity to infinity of x to the 3 dx equals, okay, let's not bother with splitting it into 2. We know the bottom one's going to minus infinity, the top one's going to infinity. Why can't I do this? Okay, the limit as t goes to infinity of, on the bottom, since I want minus infinity, let me put a negative t, that'll give me a negative infinity on the bottom, and put a positive t on top, that'll give me the positive. So I'm not splitting it up, I'm just keeping 1. And then we have x to the 3 dx. So before I go any further, do you understand the difference here? In the first one, I'm splitting it up and doing each one separately, which is what we're supposed to do. In the second one, I had the idea, well, let me just, since they're both infinity, minus infinity to infinity, let me just do it all in one, all right, and see what we get. All right, let's do this then. So this is going to be, again, the limit as t goes to infinity. Again, we do our antiderivative. That's going to be x to the 4th over 4. And it's going to be minus t to plus t. All right? So let's see. That gives us then the limit as t goes to infinity. Now let me plug in the plus t and the minus t. So I plug in the top one, that gives me t to the 4th over 4, and then we have a minus, and then I plug in my bottom limit. Now my bottom limit is a negative t, and that's going to be raised to the 4th power over 4. Well, what's minus t raised to the 4th power going to simplify to? Right, thank you, Natasha. So this is going to be the limit as t goes to infinity of t to the 4th over 4 minus t, the same thing, t to the 4th over 4. Well, those cancel out to 0. The limit of 0 is 0. So with this method, I actually get a finite number. But in reality, this thing diverges. But there is a name for what I just got here. This is called the Cauchy principal value, I believe. This is by the way, this is an FYI, okay? After the mathematician Cauchy. So this can have a use. Offhand, I don't know what it is right now, but it's not the improper integral that we are wanting to, the value that we're wanting to get at. It's a different way of doing it, but it's not the way we're going to do it. Did that help at all, Brian Hathaway? Oh, good. I'm glad the answer was yes. All right. So.
Isn't there a property where you take the integral from negative a to a of some function times 0 and
yes. If the function, okay. What Nikesha was asking was this: isn't there some kind of property where if you do the integral from minus a to a, you know, no matter how complicated that thing is, you're going to come up with 0, and that's true. If the function is an odd function, if f of minus x is equal to minus f of x, we're talking about an odd, what's called in algebra, an odd function. No matter how complicated that function is, the integral from minus a to a of this function is going to be 0. The areas will cancel out. We'll have an area over here that's positive, for example, an equivalent area over here to make negative a that's negative. The same positive area minus the negative area will cancel to 0. Yes? All right. Let's see, where are we going here? Okay, let's do another example here with this. Oh, let's do a 5-minute break. Yeah, and then we'll continue. Right. It's the same process. Here you're taking an infinite line, and somehow you're still coming up with 0. And it would be work the same way, actually. Yeah. I think that Cauchy principal value is on page 76. Let me see. It's not what we're talking about very specifically, but yeah, he certainly works at the limit on all that. But oh, that might be something. Yes, sir. Yeah, I think so. Yeah, we're talking about work, right? Yeah. I don't know. You have your calendar handy, or maybe you can see me after class. But I think when I originally did the schedule, I think I got all this stuff on Friday. And I think we can all be moving.
towards every third week.
Because notice, if you see the next test is on a Friday, chances are we're going to because otherwise we look at too much new material on the week prior to taking the test. And
I was afraid that was going to happen. Right, and we don't want to be looking at too much new stuff. Yeah, but
Looking at because the master really likes to make the yellow one. You haven't done those? Master loves, like, she likes me to give her, like, okay, like that quiz. She's like, can I have it because I want to do it? Like, she's
practice. Good.
okay, I did give her this.
Oh, you already gave her
I gave her the quiz. She's like, I love homework. I want to do this.
Oh,
But and she wants that other, yellow one too that you gave us the last time.
No, you'll have to print that out. You can print that out for our Blackboard if you're. I don't have it with me. It's a whole.
I gave her this.
Oh, it's the which one we want? We want the pink one. Oh, okay. Yeah.
She's like, I love homework. Like she loves to do.
She
it.
loves it.
Yeah,
Good.
she's so strange.
You're weird, but yeah, that's great.
yeah. I might have to talk to you at the lab.
When you do things like drugs, you got an 8 sign and then 10 sign and then negative sign and then first sign, right?
Okay, that's actually like anything that I had your wrist. Where, okay, you, what is your original view? Okay, so now this is what, okay, so you want to get everything here, what you want to do here then is basically then draw your triangle. Okay, you've got a triangle.
Let me just show you real quick. It comes from this thing right here. This means, of course, that x over 4 is equal to the sine of u, right?
Okay.
Let's draw a triangle. Let's put an angle, theta. Opposite over hypotenuse. Let's fill in. This will be 16 minus x squared, the squared, yeah. So when you're then, say, needing to get u here, well, that'll be the sine inverse, okay? When you're wanting to get a sine here, well, the sine of, wait a minute, the sine of u is our angle. This is our angle here. This is the u that you're talking about. The sine of this is going to be x over 4, not this thing here. If we draw this diagram and x over 4 is the sine of u, then just use this, and our sine of this then is going to be x over 4.
So this is just to get a triangle.
Yeah.
That's not what we're using for you.
Right.
We're just saying the angle.
Right, exactly, right. So you basically, you don't really have to do that way. You go that far. You just use this substitution, x equals 4 sine u, rewrite it a little bit down here, and then drew your picture. And that'll help you get everything in at the end. All right. Okay. So I want to do some more examples here. And this next one, we have another one of these from minus infinity to infinity examples. X to the 3 minus 3x squared dx. So first of all, we need to break it up into 2. So I'm just going to use 0 as my middle number. So I'm going to go from minus infinity to, say, 0 of x to the 3 minus 3x squared dx. And then my second one's going to go from 0 to positive infinity. Break it up. That's your first step. Okay. Now let's evaluate, say, this one. And let's see what we get. All right. So this is going to be, this is going to be the limit. Now for this first one, as t goes to negative infinity, because we have the minus infinity down below, this time we're going to have the t down below also for the negative infinity, t to 0. of our function x to the 3 minus 3x squared dx. Okay, so we now just get our antiderivative. I'm going to keep repeating that limit notation, limit as t goes to negative infinity, and the antiderivative here is going to be x to the 4 over 4, and the second one's going to come out to be x minus x to the third when I simplify it. And then our limits then are going to be t on the bottom and the 0 on top. All right, so let's plug in the limit. I'm going to keep this notation, limit as t goes to minus infinity. Now the top, when I plug in 0, I'm going to get 0 and 0, so that's 0. I put a minus sign, and then let me plug in the t. Minus t to the 4th over 4. Is it okay if I just immediately change the second minus to a plus, because I'm going to have a double minus? Is that all right? Plus t to the 3rd. I'm just taking care of that double minus. All right. So let's figure out what we get here. Now, as t is going to negative infinity. So, when t is going to negative infinity, what would an even power of t be approaching? T is getting to be bigger and bigger, more negative numbers. But now I'm raising it to the 4th power, an even power. So what will happen to all those negative numbers when I'm multiplying them together? They're going to become bigger and bigger positive numbers. So this then is going to be, but notice I do have a minus sign here. So I'm going to have a minus, but this thing is going to be going to positive infinity. I have a minus in front of it. I can't drop the minus. All right? But because it's an even power, it's going to, that second part is going to positive infinity. Now what about this one here? Now, again, t is becoming bigger, more and more negative numbers, but this time around, for that second term, I'm raising it to an odd power. No. What happens when you multiply minus 2 by minus 2 by minus 2? 3 times. You get a negative. Same thing here. Those negative numbers are going to stay negative because it's an odd power. But they're going to get more and more negative because we're going to negative infinity. So this whole part here, I've got a plus here, is going to also be a negative infinity. So negative infinity as minus, negative infinity minus infinity is going to be equal to negative infinity. We've already got negative infinity. Now we're subtracting off another infinity. We're still going to be at negative infinity. Does everybody see that? Okay. So we've done the first one, and we found out that our limit for the first one of these two is negative infinity. I don't have to do anything further with this second one right here. I already have my answer. This diverges. Okay, right there, because of the fact that the very first one already diverged. I don't have to do anything further with the second one, okay? No need to look at the second integral. We've already got our answer. All right. So we're clear on that. Once we got that, if it's broken up and we find out we don't have that much less work for ourselves, we don't have to go any further. All right, now let's look at another example. Now this time, basically, now with this example, guess what? I'm going to need to use L'Hopital's rule to figure out a limit. So that's coming back again to perhaps haunt us or whatever, however you feel about L'Hopital's rule. So here our example is from minus infinity. Now here we're just going to 0, so we don't have a double whammy. minus infinity to 0 of x e to the x dx. Okay, now to evaluate this, we have to use what rule? Or what? Nah, that won't get us anywhere. Okay, what are our two? Yeah, what are our two basic tools? Integration by parts, or some kind of clever, or maybe not so clever substitution. We have to use integration by parts. Jen, if you fiddled around with this using a U substitution, hopefully within a few minutes you'd realize that that's not getting you anywhere. Okay, so what do we want our U to equal here in this integration by parts? The whole thing? No. Just x. No, just x, really. That'll be fine. Because what do we want? We want this x in our other integral. We want this x to go away. We want it to become a 1. So if we make that our u, then in our other integral, it'll be a 1. So let u equal to, let u equal to x. So therefore, du is going to be 1 times dx, or just dx. Now, the dv is the rest of it, which is the e to the x dx. So v, what's the antiderivative of e to the x? It's just e to the x. So v is equal to e to the x. So what we get here then is, let's put the limit, let's get limit in the picture here. The limit, as this time t is going to negative infinity, all right, and now let's put a big parentheses here. We're going to put in what we get from the integration by parts. First of all, we have u times v, and that's going to be what? X times e to the x. And let's put in our limits of integration here. We're going to put the t on the bottom and the 0 on the top, because we're going to negative infinity. And then we have a minus sign. And then the next one is the v du, or second integral, and that's going to be a nice integral, because this is, again, it's going to start at t, go to 0, but our v was e to the x, but our du is just a nice dx. And so we have something we can get the antiderivative of. All right. So let's look at this then. We are going to have the limit as t goes to minus infinity. Okay, first of all, we're going to plug in a 0 here. Well, 0 times anything is going to be 0. Then we're going to have minus, and then we're going to plug in our t. Well, we're going to have an x. We put in a t there. E to the x, we're going to plug in e to the t. All right. Then, we know for this one, we know the antiderivative of e to the x is e to the x, right? We know that. So it's going to be, now we have to carry down our minus. And then here again, we're going to have, well, let me just do this like this, and then I'll write it again. We have our antiderivative, and again, our limits here are going from t to, at the bottom, to 0 on the top. All right. I don't want to do too many steps in one step, so we avoid confusion, hopefully. So we have the limit as t goes to the negative infinity of, well, the 0 we don't have to write, minus t e to the t, and then let's see what we get with this other one. Okay, I've got a minus here. We plug in our 0, e to the 0 power is 1, and then we have, then we're going to have a double minus, oops, I'm sorry, yeah. Well, actually, since we have a double minus, we're going to end up with a plus for that bottom term, and that'll be e to the t. All right? Okay. Now, let's see here. I can figure out what this limit is, and I can figure out what this limit is, but let's work with this limit here. Let's figure this out. Let's go down and figure out what is the limit as t goes to minus infinity of negative t times e to the t. Well, what happens here? When we just plug in infinity, minus infinity, this becomes in positive infinity. And e to the negative infinity, what's the limit as t goes to negative infinity of e to the t power? Very good. It's 0. It's getting smaller and smaller and smaller, so the limit is 0, and that's also on your list there. So this is an infinity times a 0 case. So if we remember from L'Hopital's rule, we can convert that into a quotient, because we can't use L'Hopital's rule with a product. So how would I want to convert this into a either 0 over 0 quotient or an infinity over infinity quotient? And there's usually a good way and then a not so good way to do this. Any ideas on how I want this thing to be represent as a quotient? How quickly we forget. Just on the last test. What do I want to keep on? What might I want to keep on top? Okay, I heard a negative t and an e to the t. And Jenna, again, it's 50-50. And we want to keep, the better thing is to keep the negative t on top. Because the derivative of negative t is so easy. It's negative 1. We want to keep it simple. And then how do I represent that e to the t, except now I'm putting it in the denominator? Right, e to the negative t. All right. And so let's figure this out then. So we then have, this is an infinity here, no, minus t, yeah, an infinity here, and then this is a double whammy. If the negative minus infinity, this also goes to infinity. So I have infinity over infinity, so I can use L'Hopital's rule. So the limit here is the derivative negative 1. The derivative of e to the minus t with the chain rule is minus e to the minus t. All right? And so what does this come out to be? T is going to negative infinity. This is actually going to positive infinity. So this goes to 1 over infinity is going to be a minus 1 over infinity. The limit's going to be 0. So this is a tough one. The limit here, using L'Hopital's rule, is 0. So we basically have 0 for this first term, minus 1 from the second term, and then plus the limit as t goes to minus infinity of e to the t. And that last one is equal, as Nikesha said, is equal to 0. So our answer here is minus 1 is our answer. So this one you had to work for, I must admit, using L'Hopital's rule, and we get a limit. Okay. Not a pretty case. I want to give you a couple of facts here that I'm not going to prove, but I expect you to remember for the exam. And that's this. 2 facts. The integral from 1 to infinity of 1 over x to the p power dx. So here, x is taken to some power. This is convergent if p is strictly bigger than 1. I.e., let's say the integral from 1 to infinity of 1 over x squared dx converges, as we already found out, where the p is bigger than 1. Please note that this x to the p is down in the denominator. Similarly, the integral from 1 to infinity of 1 over x to the 3/2 power, that also converges because 3/2 is bigger than 1, right? So this is the first fact right there. The second fact is this: the integral from 1 to infinity of 1 over x to the p power diverges if p is less than or equal to 1. We already saw that in the one example. When p is equal to 1, the integral from 1 to infinity of 1 over x to the first power, we saw that equals to infinity. Similarly, another example would be, say, how about 1 over the square root of x dx? Well, what this really is 1 to infinity of 1 over x, the square root is the 1/2 power dx. This diverges also, since 1/2, the power there, is less than 1. So those two facts need to somehow incorporate. All right. In the time we have left here, I'm going to talk about the second type of improper integral. The second type is this, where the function has a vertical asymptote for some x in the interval a to b, and in this second type, our limits of integration are finite. The limits of integration are finite numbers. So what happens in this case is that our function with a vertical asymptote, our function gets real big. It tries to approach that vertical line. So let's look at an example here of this. Example, the integral from 2 to 5 of 1 over the square root of x minus 2 dx. Now notice what happens here. When x is equal to 2, our denominator is 0. So that means we have what's called a vertical asymptote at x equal to 2. Okay. Everybody familiar with the vertical asymptote? Function gets real big. In fact, it never even has a value at the vertical asymptote. And it's usually when the denominator becomes 0. Okay, so this is how we have to handle it then. We use the limit notation again. So we do limit. Now this time, our limit is going to be approaching where we have the vertical asymptote. So our limit is approaching 2. But remember, we have two different ways that we can approach a number. We can approach it from the positive side, or we can approach it from the negative side. Here, we are approaching this 2 from the positive side because we want to approach the number 2 from above. Because this is the integral from 2 up to 5. So we want to be approaching that 2 from inside that interval. So we want to approach 2 from the positive direction. And then we put in our limit. Now our lower limit now is going to be the t, and our top limit is the number 5. of 1 over the square root of x minus 2. All right. So then again, we repeat our limit notation, limit as t approaches 2 from the positive direction, and we get our antiderivative here. And I'm not going to go through the whole process. I know you all can figure this out. Our antiderivative is going to be 2 times the square root of x minus 2. And then we're going to have our limits of integration. Again, t is on the bottom and 5 is on the top. Okay. And so therefore we plug, so what we get then is the limit as t approaches 2 from the plus side. I again repeat that. Now I fill in my top number. So it's 2 times the square root. Well, x minus 2 is going to be 5 minus 2. So 2 times the square root of 3 minus 2 times, now we're going to plug in the t for the x, the square root of t minus 2. And what are we going to get here? As t is approaching 2 from the plus side, under that integral, it's going to be getting closer and closer to what number? 0, right? It's going to be closer to 0. So this is going to go to 0 as t approaches that 2. So all we're going to be left for then for our answer is 2 times the square root of 3 by doing that limit. So therefore it converges, and that's the number it converges to. Okay. Let's do another couple of these. We have some time. I want to do these. Let's look at another one here where we have the limits from 1 to 5 of 1 over x minus 5 dx. Okay. So we look at that function 1 over x minus 5, and we know that when x is equal to 5, we've got a problem because the denominator is 0. So that's what we mean by a vertical asymptote. I'm just going to put VA. Vertical asymptote is x equal to 5. If we graph it, that's going to have an asymptote there. So we have to use our limits. This time, our number is the upper limit of integration. So we still use the limit and the t notation, but this time t is now approaching that upper number 5, but because it's the upper number, we're approaching it from below. So I'm going to put a minus there after the 5. We're approaching it from down below of the integral from the bottom number is 1, our top number is the t, of 1 over x minus 5 dx. All right. Now I think we all can get that antiderivative, so let me again repeat my limit notation. The limit as t approaches 5 from the minus side. Okay, our antiderivative of 1 over x minus 5, figure that out. That's going to be the natural log of the absolute value of x minus 5. And then we put our limits here. The bottom one is 1. The top one is the t. Okay. Now let's plug things in here. We have the limit again. Again, we carry this down. Plug in our top one, which is the t. So that's the ln of t minus 5 minus the ln, and now we plug in a 1 for the x, 1 minus 5. But notice here that that's an absolute value because we can't do the ln of a negative number. But the antiderivative has the absolute value there. All right. So, as t approaches 5 from below and gets closer and closer to 5, what is this little expression going to get closer and closer and closer to? Yeah, 0. T is getting closer and closer to 5, so t minus 5 is getting closer and closer to 0. Let me put a little arrow here. Approaching 0. And it's approaching 0 from the positive direction, because t is approaching 5 from the, no, I'm sorry. It's approaching it from the negative direction. Never mind. But because it's an absolute value, it's going to be a positive number. But it's going to be smaller and smaller to approaching 0. So what happens here when we do a natural log of something of a number that's getting closer and closer to 0? What's our natural log go to? Very good, negative infinity. So this first limit is negative infinity, and then we have minus the ln of 4. Well, this thing then diverges. Okay? All right. I have to get to the comparison theory here. Let's do this example here. There is stuff here about when we have the vertical asymptote in the middle, and I'll just mention this. Say we have 0 to 8 of 1 over x minus 4 dx. Remember, here our vertical asymptote is at x equals to 4. So I actually have to split this up into 2 parts. So I have to split it up into 0 to 4, and then from 4 to 8. And then work each one individually, because I happen to have that vertical asymptote in between my 2 limit numbers. All right? So work each individually. Work each one individually. And again, remember, if the first one diverges, you can stop right there. If the first one diverges, which in this case it will, if the first one diverges, you can stop and it diverges. Okay. The last little thing here in this section is called the comparison theorem, and it's a really kind of nice way to handle some things that might be kind of difficult. Let me write it down and then show you how it works in a couple of examples. Okay, so here we have, suppose f of x is bigger than or equal to the function g of x, and g of x is bigger than or equal to 0. So these are 2 positive valued functions, but one of them is always less than or equal to the other one. All right. Then, let's say that this is the case for x bigger than or equal to a. We have this nice comparison. All right, so then, if the bigger one converges, then the smaller one will also converge. So we have this. If the integral from a to infinity of the bigger one if that converges, since it's bigger, we know that the smaller one will converge. Then the integral from a to infinity of the smaller one also converges. And I think that makes intuitive sense. If the bigger one converges to a positive number, certainly a function that's less than that is also going to converge to a positive number. I think it makes kind of sense. And we also then have it this. Well, what if the smaller one diverges, then we know that the bigger one will also diverge. So if a to infinity of g of x, this is the smaller one, diverges, well, then the bigger one is also going to diverge. Then the integral from a to infinity of the bigger one also diverges. This is the bigger one. All right. So let me just show, I think we have time for at least one example of this. Let's figure this out. Let's say you're told to evaluate 1 to infinity of e to the x over x dx. Now, if you remember from the very beginning of class, e to the x over x dx is one of those functions that we can't get ordinarily an antiderivative for. Can't find the antiderivative. Well, we can use the comparison theorem. Let's try the comparison theorem. What does, and we saw this example earlier, the integral from 1 to infinity of 1 over x dx, does that converge or does that diverge? It diverges. We saw that earlier. Now, e to the x is going to be bigger than 1, right? When x is bigger than or equal to 1, e to the x power is going to be bigger than the number 1. It starts with e squared, e to the third. It starts to become a really big number. So, e to the x over x is going to be bigger than 1 over x when x is bigger than or equal to 1. If the numerator is bigger, we have the same denominator, we can say that e to the x over x is bigger than the other one. Does that make sense? We know that this one diverges. So without even evaluating the antiderivative, thus, 1 to infinity of e to the x over x dx diverges by the comparison theorem. All right, just from comparing. I want to do one more. But you see this. Okay, let's look at one more comparison. Let's look at, again, from 1 to infinity, of, say, 1 over, let's see if this is going to be, okay, 1 over x to the 5th plus 10 dx. Okay. Now, I want to compare it to the integral from 1 to infinity of 1 over x to the 5th dx. First of all, will this 1 over x to the 5th, will it converge or diverge? It will converge. Here is that p, that formula p that we had. P is bigger than 1, so it's going to converge. All right. Now, do we agree that x to the 5th plus 10 is bigger than x to the 5th? Do we agree on that inequality? Okay. So since it's bigger than it, If I flip it and do a reciprocal, 1 over x to the 5th plus 10, I'm going to flip my inequality, and that's going to be less than 1 over x to the 5th. Because the denominator is going to be bigger, that means the value altogether is going to be smaller. All right, so we see that? Denominator is bigger, value is smaller. So this converges. So I can just do the comparison test. This is something smaller, so it's also going to converge. Thus, 1 to infinity of 1 over x to the 5th plus 10 dx converges. This integral, by the way, so we all kind of see that through the comparison test, I hope. By the way, just getting the antiderivative, let's not, of 1 over x to the 5th plus 10 dx, that would be a very interesting process. That is not something simple at all. All right. In fact, I plugged that into my computer system Maple and got this humongous, ugly expression out. All right. So it is not a pretty kind of antiderivative to get. But if we can use this comparison test, we can at least know that this improper integral converges, and we don't have to mess with doing all of that. All right? And you will see that on the exams, this kind of thing. All right. Okay, that finishes everything then for the test. So you have the things that you need. If you have any questions, you can certainly email me. Monday, we are going to start on chapter 11. We are going to spend the 50 minutes on that. I know, I see that look there, Cassandra. I do see it. All right. And that's a whole new thing that we're going to start. It's about series, so I think maybe some of us have got a little integration overload, maybe. I don't know. Maybe. I'm just taking a stab at it. So it's going to be a different kind of topic for a while, and I think maybe it'll be a nice change of pace a little bit. So anyway, have a nice weekend. That's it.
Yeah, I'd also forgotten to carry the 2U. I forgot I had to substitute the 2U. So when you have that 2U, then how do you get your
Okay. That's a real good question. So we have to use the trig formula. The sign of 2U can be the same as 2 times the sine of the U times the cosine of the U. So what we have to do here in your antiderivative then is replace this with minus 4 times 2 sine U cosine U. Okay? And then we have our nice little triangle here with U that you did. So we have x here, 4 here, square root of 16 minus x squared there.
So the opposite over that top.
Yeah, so this will be replaced by x over 4, but this, because it's just plain u, is going to be replaced by square root of 16 minus x squared also over the 4. And then you simplify, you can cancel out a couple numbers and all that. But that's what you have to do here, because you don't have a 2u, you just have a u. But you're going to use this kind of identity. Okay. Yeah. I have a question. Yes, sir. Discrete math. Do you recommend me taking that with calculus? What do you want to get into? Engineering. Like or whatnot? Well, it might be good for you. Well, with calculus, questions with calculus. Well, that's a lot. That's a lot.
So you know what your work schedule is and your other schedule is. Cal 3's is probably going to take us, I'm not quite sure how much time we're spending on Cal 2. A lot more. Okay, but it's going to take more time. You might want to hold off on it because you don't want to overburden yourself and find out you're suddenly paying for a class that you don't have any time for. I think eventually, though, I mean, you're young and you're just starting out. Eventually, I think it would be a good class to take either here or anywhere else you're going to go, because it's got lots of stuff in it in fact, you might find that it may or may not be required once you get to a 4-year school. You know, you'll have to see whether or not with your